The elements and compounds that sustain life are constantly moving, cycling endlessly through living things and the environment. But when human activities interfere with these natural flows, changing their rates or storage times, the environment can no longer process them properly. That's when these materials turn into pollutants. On a global scale, this process is known as biogeochemical cycling, the continuous transport and transformation of substances through the air, water, land, and even ice. Water is essential to life. That's why, when astronomers search for signs of life on distant planets, they always look for one thing: water. Most of Earth's water is stored in the oceans, but thanks to the power of the sun, it never stays still. Solar energy constantly evaporates water, and winds carry it all around the world. This endless movement is called the hydrologic cycle, the circulation of water within Earth's hydrosphere. It involves changes in water's physical state, from liquid to solid to gas, and back again. It's a continuous exchange between the atmosphere, the land, the surface and underground waters, and even living organisms. Within this grand cycle, there are four main physical processes that drive the movement of water: evaporation, precipitation, infiltration, and runoff, along with subsurface flow. Evaporation, the process where water from oceans, lakes, and rivers changes from liquid to gas, rising into the atmosphere. Transpiration, the release of water vapor from plants. Together, evaporation and transpiration are called evapotranspiration. Precipitation, moisture that falls from the sky as rain, snow, hail, or fog. Infiltration, when surface water soaks into the ground, depending on the soil or rock's ability to absorb it. Runoff, water flowing over the land, moving downhill through streams and rivers toward the oceans. And subsurface flow, water that travels underground, slowly making its way back to the surface or the sea. Carbon plays a vital role in sustaining life. It serves two main purposes for all living organisms. It builds the structure of organic molecules, and it provides the chemical energy needed for metabolism. The carbon cycle begins with photosynthetic organisms, like plants, taking in carbon dioxide from the air. This process, called carbon fixation, transforms gaseous CO2 into organic molecules that living things can use. Through this continuous movement, carbon flows between the biosphere, atmosphere, oceans, and the geosphere. Plants absorb carbon dioxide and, through photosynthesis, store carbon in their tissues. Producers and consumers, like animals, then release some of this carbon back into the air through respiration. Meanwhile, decomposers break down dead plants and animals, returning even more carbon to the atmosphere. Another major exchange happens between the oceans and the atmosphere. Carbon dioxide dissolves in seawater, where marine life uses it for photosynthesis, continuing the global exchange of carbon. Two major human-driven processes also affect the carbon cycle: fossil fuel burning and land use changes. When we burn coal, oil, or natural gas for energy, massive amounts of CO2 are released into the air. Changing how we use land, such as through agriculture, deforestation, or reforestation, also alters how carbon moves and is stored on Earth. Today, the global carbon cycle is no longer in balance. Atmospheric carbon dioxide levels are rising rapidly, now about 25% higher than before the Industrial Revolution. This imbalance fuels global climate change. It moves among several reservoirs: the atmosphere, land, oceans, and sediments that include fossil fuels. These exchanges occur through a mix of chemical, physical, geological, and biological processes. Although the oceans hold the largest pool of carbon near Earth's surface, most of it is not part of the rapid exchanges with the atmosphere. In essence, the carbon cycle connects every living and non-living part of our planet. But when this balance is disturbed, it reminds us how deeply human actions are tied to Earth's climate and future. Nitrogen is one of the most important elements for life. It's a key component of proteins and DNA, the very molecules that make up all living things. When organisms die or when plants and animals shed parts of themselves, like leaves, feathers, or skin, nitrogen re-enters the environment. Fungi and bacteria break down this organic matter, releasing ammonia and ammonium ions back into the soil. Animals also return nitrogen through their waste products, such as excrement and urine. The role of bacteria in this cycle is crucial. They make nitrogen available in forms that plants and animals can use. All nitrogen that animals obtain can be traced back to plants, directly or indirectly through the food chain. Plants absorb nitrogen from the soil through their roots, mainly in the form of nitrate ions, NO3-, or ammonia, NH3. Ammonium ions tend to cling to soil and clay particles, but nitrates, being negatively charged, dissolve easily in water. Because of this, they can be washed into rivers and lakes, leading to eutrophication, a condition that promotes excessive algae growth and harms aquatic life. Human activities have greatly altered the nitrogen cycle. The overuse of fertilizers has led to pollution and eutrophication. The burning of fossil fuels releases nitrogen oxides into the atmosphere, and denitrification, carried out by bacteria like Thiobacillus denitrificans, converts nitrates back into nitrogen gas, completing the cycle. The nitrogen cycle reminds us how interconnected life and the environment truly are, and how vital it is to protect these natural processes that sustain all living things. The phosphorus cycle begins when phosphorus compounds slowly leach from rocks and minerals over long periods of time. Unlike other cycles, it has no atmospheric form. Instead, phosphorus is transported through water and eventually returned to the environment through the process of decomposition. The phosphorus cycle starts when phosphates from rocks and ocean sediments are released through weathering. Plants absorb these phosphates from the soil, and animals get them by eating plants. When organisms die, phosphates return to the soil or water. Phosphorus is essential. It's found in DNA, bones, and cell membranes. However, too much phosphate in water can cause algal blooms that harm aquatic life. The sulfur cycle plays a vital role in living organisms as a minor but essential part of proteins. Most of Earth's sulfur is stored underground in rocks and minerals. It's released into the air and water through weathering, volcanic eruptions, and seafloor vents. Human activities, like burning fossil fuels, also add sulfur to the atmosphere, leading to acid rain that affects soil and water quality. The sulfur cycle is vital for life and the environment. Sulfur is a key part of proteins and vitamins. Plants absorb it from water, and animals get it by eating those plants. Most sulfur is stored in rocks or deep ocean sediments, but it can also enter the atmosphere through volcanic eruptions, decaying organisms, and evaporation. When sulfur dioxide is released into the air, it reacts to form sulfuric acid, which falls back to Earth as acid rain. This affects human health, damages buildings, and harms vegetation. Yet sulfur particles can also reflect sunlight, creating clouds that slightly cool the atmosphere, continuing the natural sulfur cycle. The biogeochemical cycles are the Earth's natural systems, continuously recycling the elements that sustain all life. They keep our planet's climate and ecosystems in balance. But when human activities like pollution, deforestation, and industrialization interfere with these cycles, that balance begins to break down. To protect the Earth's natural equilibrium, we must commit to sustainable practices, using our resources wisely, caring for our environment, and working together to preserve the cycles that give us life. Because when we protect these natural processes, we're not just saving the planet, we're securing the future for every living being that calls it home.